So I would like to start welcoming you all to the 20th webinar of the graduate program in physics of the Federal University of Pará in Amazonia, Brazil. I ask everyone to kindly leave the audio and video streams turned off, except for the moment you're going to speak. Questions will be allowed after the webinar, unless otherwise requested by the speaker. The questions can be asked using the chat. Today, we have the honor to listen to Professor Geoffrey Turok, who is the inaugural holder of the Higgs Chair of Theoretical Physics at the University of Edinburgh in Scotland, United Kingdom. Professor Neil has received various awards and distinctions, including the 1992 James Clerk Maxwell Medal of the Institute of Physics from the United Kingdom and the 2008 TED Prize for his work in mathematical physics and in establishing the African Institute for Mathematical Science, AIMS, which he founded in South Africa in 2003. Since then, AIMS has grown into a network of 5 centers spanning the African continent. AIMS graduates over 300 students per year at master's level, and over 700 of its graduates have gone on to PhDs. In 2016, Neil was awarded the John Torrance State Medal for International Leadership in Physics by the American Institute of Physics. In the same year, he was made an honorary fellow of the Institute of Physics in the United Kingdom. In 2018, Neil was named an officer of the Order of Canada in recognition of his substantial contributions as a scientist to the field of theoretical physics and cosmology. He served as director of the Perimeter Institute for Theoretical Physics in Canada from 2008 to 2019, in recognition of which he was awarded the title of Director Emeritus of Perimeter. He also founded the Center for the Universe at Perimeter Institute, a research center devoted to cosmology. Neil obtained his PhD in 1983 at Imperial College in London under the direction of Professor David Ian Olive, one of the founders of the superstring theory. Professor Neil is known worldwide for his relevant scientific contributions to mathematical physics and early universe physics, focusing on observational tests of fundamental physics in cosmology. Among several books, Professor Neil authored The Universe Within, From Quantum to Cosmos, containing 5 lectures delivered across Canada and broadcast on Canada's National Radio Service, the CBC. For his book, he received Canada's top prize for popular science writing. Well, we are here today to listen to Professor Turok, so I should not take more of your time with this introduction. Professor Turok, thank you very much once again for having accepted our invitation. The audience is yours.
Thank you very much, Luis, and thank you for inviting me to give this lecture. This is a very strange time in many ways. I just moved to Scotland 2 months ago, and it's been very difficult to meet with people. We're all suffering in our isolation, so I'm sure many of you are going through the similar problem. So just by way of entertaining you, I thought at the beginning I would introduce somebody to you who's also in the audience. That's my dog, Sunshine. And when she goes to sleep, I will realize that I'm getting boring. Okay. Okay, so I'm going to show my slides, and I'll just check. Luis will tell me if it's working. Okay, so here are the slides. Can you all see those?
Yes. Perfect.
Okay, great. So the topic of the talk today is quite varied. I'm going to tell you about the role of quantum mechanics in the universe. And so from the title, you can probably tell this is going to involve very large things and also very small things. In fact, the great frontier of theoretical physics today is to reconcile both of those. We've got incredibly successful experiments which have tested particle physics, and which is, of course, fully quantum at the Large Hadron Collider. And everyone was surprised at how successful the minimal theory has been, the standard model. We also have amazing experiments verifying Einstein's theory of gravity on large scales, from black holes to galaxies to the whole cosmos. What we do not have is a theory which reconciles both of these, the large and the small. As human beings, we sit in the middle. We are the most complicated things we know of in the universe. And in many ways, we live right between these two extremes, the very small, the very large, and our job is to reconcile them. So the theme of the talk is extremely simple, and it's something you all know from undergraduate physics, if not before, which is the idea of interference, that waves can interfere. In quantum mechanics, this is the fundamental concept, and I've put the I in blue because the really new feature about quantum mechanics as compared to classical is that the complex numbers play a crucial role, and you're going to see that throughout this talk. The imaginary number I, of course, was a huge advance in mathematics. Its introduction allowed the solution of many equations which could not previously be solved, but in physics, it enters right in the heart of quantum physics, and its entrance is involved in this phenomenon of interference, in which amplitudes can cancel, and this is a very subtle and rich phenomenon, and leads to many of the most bizarre features of quantum physics. It's universal, and I'm going to show you some interference patterns on astronomical scales, and how the same principles which govern quantum physics are required to calculate these interference patterns, which can now be observed in radio astronomy, for example. So here it is, all the known laws of physics. It's somewhat surprising that you can combine all of them into a single line. They are deeply consistent. The same themes recur across the whole span of physics. And so this is a formula called Feynman's path integral, through which we express quantum mechanical amplitudes in terms of the classical laws which correspond to them. So we see Euler's number E right in the middle of the formula, and the imaginary number I. And so all of physics is really a giant interference pattern. And the quantity governing the phase of that exponential is the action, which incorporates gravity, gauge theories, particle physics, and of course the Higgs boson, and the dark energy, which is the potential energy. You can think of it as being the minimum of the potential energy of the Higgs field. So now this way of writing the laws I found very inspiring when I was a student, to realize there's really not that much to learn about physics. All you have to do is to learn what this formula means, and that's very good for someone with a bad memory like me. You don't need to remember any details. Physics is not like biology or history. Physics is incredibly unified and logical, and based on a small number of very simple principles. The difficult thing about physics often is it's really hard to calculate what these formulae imply. And in this case, although we know all the laws of physics, here they are, there is nobody who is able to derive certain physical phenomena from this law. For example, we'd like to know what happens when a black hole evaporates, and how is information lost? The answer, I believe, is right there in front of us. It's in this formula, but one has to be able to calculate, and essentially that amounts to doing a very difficult integral, and so far we're unable to do that. So new techniques for being able to manage this formula are really important, and I will describe those today. I've listed what psi is. This emphasizes that the formula is very compact notation. The psi in the action is the set of all particles, fermions, and so there are 16 of those, we believe, if you include the right-handed neutrinos. And I just want to make a very simple point. You know, I used to show this formula with the caveat that the one ingredient of the universe we didn't know how it fit into the formula was the dark matter. But then 2 years ago, with my colleagues, Latham Boyle and Kieran Finn, we realized that the simplest candidate for the dark matter is actually one of the right-handed neutrinos. And I may talk a little bit about that later. But for me, that was, you know, it's a possibility, hasn't been proven yet. It's got a very clear prediction if it's true. But for me, that was a revelation. It was to say, you know, maybe we do know the laws of physics. Maybe this is really the end of the story. We don't need extra dimensions. We don't need extra particles. Maybe we really have seen everything. What we have to do now is to understand how to use these laws to understand nature. And I've really changed in the last few years towards emphasizing the foundational and simple and economical nature of the laws that we know, and that I believe a lot is buried in those laws, which we will, if we look closely enough, we'll see they will already solve the puzzles we worry about. Now, one of the most interesting things to think about is how so I wrote down this formula, which includes quantum mechanics, Planck's constant, and gravity, Einstein's theory of gravity. So this formula describes quantum gravity. Now, how? Well, this was conceptualized by John Wheeler, who was Feynman's PhD advisor, of course. And John Wheeler invented the topic called quantum geometrodynamics. So this is the most challenging problem in quantum physics, namely, what happens when space-time itself becomes quantum? How can you even describe physics when the arena in which physics is occurring is quantum mechanical? So we live in a superposition of space-times, not in a single classical space-time. So this was his vision. He wrote some beautiful heuristic papers about this. It's an idea which has never gone away, and I think it was revived by string theory. String theory is a sort of toy model for this because it's a two-dimensional quantum geometry, theory of two-dimensional quantum geometries, which absolutely realizes Wheeler's vision, but it's only a toy model. And you know, the way I got into this was from a Latin American theoretical physicist, Claudio Teitelbaum, who's in Chile, of course, and he really wrote the best papers on this topic in the early 80s. Some very beautiful formal papers on trying to carefully define the path integral over 4 geometries. And since then, we became very good friends, and I visited Claudio, and much of what I say actually will be inspired by his point of view. Claudio, by the way, had Wheeler as his advisor, and of course interacted strongly with Feynman. And so this is a very well-defined theoretical, let's say, what's the word? Lineage. Okay, so we have to do this integral. It's a crazy integral. First thing is it's infinite dimensional, and we must sum over space-times. But let's deal with one of the most elementary aspects of this integral first, which is that it's an integral over a phase. And this phase is extremely oscillatory. So we have to learn how to do oscillatory integrals. And rather remarkably, physicists have avoided this problem for decades with a certain trick called a Wick rotation. And this Wick rotation well, I won't dwell on it a great deal, except to say that it does not work for gravity. And so in my view, the Wick rotation got people into a lot of trouble. What we have to do is actually understand interference, where the I is in the formula. You know, in brief, what people did, including Stephen Hawking, was get rid of that I by replacing integral dt, the part of the action involving an integral over time, by saying that t should run up the imaginary axis. So if dt goes to actually minus I d tau, where tau is real Euclidean time, then the i's cancel. And what you end up, instead of interference, you get a statistical physics distribution, a Boltzmann distribution. And for some purposes, like for doing lattice QCD, that's a very good trick. It enables you to put this on a computer, and you forget about all these phases. You just do stat mech. But unfortunately, that trick doesn't work for gravity. The gravitational Euclidean action is not positive, and there are lots of other problems. It also doesn't work for describing dynamics, because when you make time imaginary, you lose the ability to define the initial and the final state at some definite time. And so you end up doing equilibrium physics rather than non-equilibrium. The universe is not in equilibrium, and so you're unable to describe the universe. So that's to say, we have to figure out how to do these oscillatory integrals without removing time. So let's do a very trivial example, the Fresnel integral. It's integral of e to the I x squared. And as a physicist, your first, so, you know, what is that integral? Well, the integrand has magnitude 1, and it oscillates faster and faster as x goes off to infinity. So, you know, good luck putting that on a computer. You will have trouble to make sure all of those oscillations are taken care of properly. So as a physicist, what your first instinct might be to cut off the integral at x equals plus or minus r, and then define the integral as the limit r goes to infinity of that finite integral. It has a good limit. It's just e to the I pi over 4 times the square root of pi. And you can even type this into Mathematica, plot the answer. That's what I've done in this plot. And you will see that as r increases, when r equals 0, the integral is 0. As it increases, it converges on this point in the complex plane. The integral is a complex number. And so everything looks good. But notice this integral is only conditionally convergent, namely, if I took the magnitude of the integrand, the integral would definitely not converge. It only converges because of the oscillations. And that's a hint of how important these oscillations are. They actually make things well defined. It is the interference which causes us to be able to predict things in physics. And this theme will occur again and again. It's the oscillations, and handling them properly is really the key to understanding quantum physics. Now, one-dimensional integral is all very well, but we've got to go to higher dimensions, and in particular, the path integral is infinite dimensional. So let's at least go to 2 dimensions, and we immediately see a new phenomenon. So I've got a 2-dimensional integral, e to the I, let's say x squared plus y squared. I'm in 2 dimensions. I want to cut off this integral. Well, the difference between 2 and 1 dimensions is that the shape of the cutoff is now free. So I could choose a square cutoff, just cutting off x and y in the same way I did the 1-dimensional integral. And then the integral, of course, is just the square of the previous answer, just the square of this answer. But I could have chosen a round integral. I could have I could have re-expressed x and y in terms of r, the radius. And then since the integrand is circularly symmetric, cylindrically symmetric, the angular integral is trivial. And so now I do the radial integral. Well, you can do the radial integral exactly. It's given by the right-hand side. But you can quickly see that has no limit. As r goes to infinity, the integral certainly does not converge. It just oscillates forever. So this cutoff trick fails miserably in 2 dimensions. Namely, your answer will depend on the shape of the cutoff. And that's very worrying indeed. Indeed, it's problems like this that led people to the Wick rotation as a cure for quantum physics. But you see, the Wick rotation is really the wrong thing to do. What you're doing is rotating time, but time in quantum physics is a given. I mean, we study the dynamics of a system in time. You really shouldn't rotate the time. What you should do is rotate the degrees of freedom you're integrating over. And that's what we'll do. So we won't do Wick rotation. We're going to actually do contour deformation of the integral of the variables you're actually integrating over in the path integral, right? So the path integral is an integral. I haven't even told you what the variables are, but they include the metric, the fields, they're quantities you're path integrating over. And those are the things you should be continuing into the complex plane. Let me show you a couple of other quick examples. Don't worry if the formulae look a little bit complicated. All I'm doing here is going to higher dimensions. We want to go to infinite dimensions. So let's go to d dimensions in the integral. And I'll assume that the action, instead of being x squared, is going to be x, or just radius to the mth power, where m is some integer. I just want to see qualitatively what this kind of integral looks like, and I'm interested in d being very large, so large dimension. Now you can see immediately this integral with a round cutoff, it's a pretty strange thing because the integrand is diverging as the radius becomes large. The magnitude is diverging like little r to the d-1, and then you have this oscillatory phase. So is this integral well defined or not? So I think most people would just give up at this point, but that's actually the wrong thing to do. Let's just calculate the integral. And what we see is that at large capital R, at large cutoff, it has a very simple character. There's a leading term, which is independent of capital R. And then there's the next term, which diverges at large R, but in such a way as it oscillates very, very fast as R gets large. Well, can I remove those oscillations? And yes, and I believe this is the way the natural world works, is, when I throw a ball from me to you, indeed, it can go to the moon and back. That's what Feynman's path integral tells you. There's nothing to stop the ball, and quantum mechanically, the ball goes to the moon and back, or it goes to Jupiter. However, those paths, those extreme paths, all cancel out because of the oscillatory nature of the integral. Now, what does that mean? It means when you deal with this integral, you should not use a sharp cutoff. You should use a smooth cutoff, which enables those oscillations to happen. So that however I'm controlling this integral, the ball that goes to the moon and back will not be a big contribution to the answer. So in the last line, I write what happens in d dimensions with a smooth cutoff. So here, just for convenience, I pick e to the minus r, little r over capital R to the power m, something that will smoothly go to 0 at large radius. And now we can do this integral, and we discover something very nice, which is I get the same leading term, but now the subleading terms fall like inverse powers of capital R. So indeed, as capital R goes to infinity, what happens is all those violent oscillations have cancelled themselves out, and I get a completely well-defined answer. And by the way, there's a very nice book about electromagnetism, in which similar divergences occur. When you add up the fields and forces due to charged particles, for example, there are similar subtle cancellations, and the way to resolve them is to smoothly cut off the integrals in such a way as to allow those cancellations to occur naturally. But as far as I know, before this work, this kind of approach was not discussed in quantum physics at all. It's a very elementary mathematical point, but it seems to have been overlooked. So a question, now it's sort of ugly, introducing a cutoff is ugly, even if it probably is close to the real physics, of why we don't, when we throw a ball between each other, we don't see the effect of the moon. So how do can we implement this mathematically without explicitly introducing a cutoff? And so can we get the result for an infinite smooth cutoff without introducing a cutoff at all? And the answer is that we can. And in fact, it's done in a very beautiful way by complex analysis and the Cauchy Theorem. So imagine, for example, I'm doing an integral e to the I x to the fourth, right, over the real x-axis. Okay, so a complex number. It's a non-trivial integral, and it really oscillates incredibly fast as you go to large x, stronger than the e to the I x squared. Now, I have in mind that I'm going to cut this off with some smooth cutoff function. And let's imagine that cutoff function is singular only at infinity in the complex x-plane. Okay, so it's a particular kind of smooth function. It's called an entire function. So it's going to be analytic everywhere in the complex plane except at infinity. Well, if you're trying to do that integral, there's a nice way to proceed, which is to deform the contour in x from the real axis, the physical one, into the complex plane in such a way as the integral converges. So obviously, if x is rotated slightly into the positive imaginary half plane at positive x and in the lower half plane at negative x, what happens is the integral now decays exponentially at the two ends, and the integral becomes absolutely convergent. Now, there's a further step. You have to show that the segments of the integral, the little green segments, actually vanish as the radius is taken to infinity. And that's a little calculation in analysis. It's not hard to show. And that shows that the original integral actually equals the deformed integral. And the deformed integral is much easier to calculate. And it's being absolutely convergent. All kinds of nice properties follow. For example, physicists typically assume in multidimensional integrals that the answer is independent of the order in which you perform the integrals. Okay, we usually just taught that and we perform it, and we just expect that. And so, for example, in Feynman's book on path integrals, this is just assumed that integrals, discretized path integrals, the answer will be the same no matter which order you perform the integral. But this is in fact not the case. It is only guaranteed if you've made the integral convergent, absolutely convergent, before you perform the subintegrals. There is, it turns out, a beautiful mathematics for performing highly oscillatory integrals exactly. The way it's done is by steepest descent. So you find saddle points in the complex plane, you deform the original contour onto these steepest descent contours. And there's a whole mathematics for how to do it. It works in arbitrary finite dimension. It's called Picard-Lefschetz theory. And you will find in the recent literature quite a few papers on using Picard-Lefschetz theory. Our work is a little bit different than most of these works. You see, often physicists will proceed by finding saddle points and then trying to decide if those saddle points are relevant to the original contour integral. Now, the trouble is with any interesting integral, especially an infinite dimensional one, there are going to be very, very many saddle points. For infinite dimensional integrals, there generically are infinitely many saddle points. And so enumerating all these saddle points is very laborious. Picard-Lefschetz have a beautiful theorem to tell you how to decide which saddle points are relevant or not relevant. But we took a slightly different approach, which is literally to flow the contour. You start with your contour on the real x-axis, and you flow it downhill. Downhill means take the magnitude of the integrand and flow your contour to minimize that magnitude. And this turns out to be a beautiful technique, allows you to transform this highly oscillatory integral into a series of integrals, which are defined by these saddle points. Every saddle point corresponds to what's called a Lefschetz thimble, which is a absolutely convergent integral, which is bell-shaped. The integrand is bell-shaped. At the end of this talk, I'm going to tell you we have a new way to define Lorentzian path integrals. It's a sort of embarrassment, enduring embarrassment to physics, that although this is the way to represent all of physics, we don't know if these integrals exist. They've never been shown to exist, except if you do the Wick rotation, which, as I mentioned, basically removes time and stops you understanding dynamics and doesn't work for gravity. So, so we have used this Picard-Lefschetz approach to define Lorentzian path integrals. Now, I think I'll stop there and just ask if there are any questions.
Okay, thank you. So far, I mean, we have no questions registered in the chat.
Okay.
So
Okay.
if you want, you can move forward.
All
and
right.
People, because normally nobody asks for questions in the middle of the presentation. So maybe it was my fault.
Well, I love questions. So if you either do a chat or just interrupt, I will be very happy. So please don't hold back. But what I'm going to show you now is an application. We were very surprised. In fact, one of our colleagues in radio astronomy, you probably have heard there have been some very exciting developments in radio astronomy with the discovery of fast radio bursts and also many pulsars. So these are coherent sources of light, except it's in the radio wavelengths. Coherent sources all the way across the universe. They shine at us. They emit coherent light as a wave, and it travels all the way to us, and then we receive it in radio telescopes. As it travels, these radio waves interfere. They are deflected by charged plasmas or gravitational fields on their path to us. And what is actually detected by the radio telescope is the interference pattern created by these lenses along the line of sight. So one way of saying it is that in the universe, the double slit experiment of quantum mechanics is happening the whole time. And in fact, radio astronomy, the whole field, is just studying it's not the double slit anymore, it's a multiple slit, and the slits are all complicated shapes and so on. But that's the field of radio astronomy. So we realized that our approach to path integrals allowed us to make predictions for what radio telescopes would see. And indeed, in radio astronomy, the astronomers were trying to compute interference patterns by doing oscillatory integrals. It's the same integral you have to do when you do the path integral. It's not surprising because it's light, and light is described by a path integral. So these are called Fresnel-Kirchhoff integrals in radio astronomy, but we actually derive them from the Feynman path integral. They're really the same thing, and the interference patterns are simply quantum mechanical interference. You can think of these as solutions of the Maxwell equations. You can think of them as waves, but you don't have to think of it that way. You can think of it as individual photons, each one of which is really a quantum particle. And as it travels, its amplitude is described by the Feynman path integral. And that gives you a way to describe wave interference, which is actually more fundamental than Maxwell equations. So here it is. I won't give you the derivation. You can read in our paper how directly from the relativistic action from of a massless particle, i.e. a photon, you can, and if it's traveling through a plasma, you can derive essentially the path integral. And the path integral, if we have a thin lens, so the picture here shows, for example, a plasma which we approximate as simply sitting in a sheet. So we sit at x ob, the observer position. We're looking at a source at xs. And then in the plane in between us, there is a plasma on that horizontal line with the dots. That's a plasma. And the photons can take different paths. The paths are kind of trivial outside the lens. They just straight line paths, but they get bent at the lens and they pick up a phase, which is given by the formula above, and it follows directly from the path integral, that phase. So part of the phase you pick up is a Pythagoras term. It's just the Euclidean path length of the path, these two straight lines. Because they bend, they're a bit longer than a really straight line, and that gives you a contribution to the phase called the Pythagoras contribution. And the second contribution is the phase you pick up in passing through the lens, and that depends on the basically depends on the electron density in that plasma sheet, which comprises the lens. So end of the day, to get the interference pattern, you just do this path integral. In this case, it's an ordinary integral, multidimensional, depends on, in this case, it would be two-dimensional, with some complicated function in the exponent. First thing you realize when you think about lensing is you get the formation of caustics. This is a picture in the wave optics. If I treat ray optics. If I treat light using ray optics, then I just have a bunch of rays. They can be bent by a lens, and then you get overlaps called folds. And at the fold itself, you know, when you observe, you see a spike in the intensity. These are called caustic spikes. So this is all familiar from classical optics. But what happens when you include wave effects is these caustics are become more intricate because of diffraction. So you don't get infinite intensity at a caustic. Instead, the infinity is controlled by the diffraction effects in the light. So let's just do an example. Imagine this phase. It has a Pythagorean term, x minus mu all squared. And it has a second term, which would be a localized. This is a Lorentzian lens, for example, with some strength alpha. So all I'm going to do is integral dx e to the I phi of x. And I have to do this integral. So it's a nasty integral. It cannot be done analytically. but it encodes these caustics, it encodes diffraction. So what it means mathematically is as I dial mu, which is the observational parameter, my observational plane, I would measure the intensity as a function of mu, and then alpha is the strength of the lens, and you can see if alpha is very small, the lens is weak. Basically, there are no caustics, and I just get the effect of the lens is small and nothing interesting qualitatively, no qualitative effects. As I dial up alpha, suddenly I create these caustics, and you get spikes in the intensity, multiple images, etc. So the number of so I'm trying to do that oscillatory integral. It turns out that the number of images in geometric optics is just the number of real saddles. So I'm integrating over x. There may be saddle points on the real x-axis. These correspond to real classical paths, and there may be more than one. And if there are three, then there are three images that are three. Yeah, so there are three possible classical paths for the light to take, and that corresponds to three images of the same source in the image plane. So here's how we do the integral, okay? We start with it, we want to do the integral along the real x-axis. And let's say there were three saddle points, so three real images of the lensed object. Well, how am I going to do the integral? What I do, so just watch the movie, I'm flowing the contour from the real axis downhill onto the steepest descent contours of each of those three saddle points. So you see that my original integral equals, Cauchy's theorem tells you that two integrals are equal, the initial one and the final one. They're equal because in Cauchy's theorem I can deform the contour however I like and I'll get the same integral. The gray areas are the areas where the integrand becomes exponentially small. And it tends to zero at the singularities. They may be at infinite x, or they may be at finite x, in this case on the 2 points on the imaginary axis. So basically the contour flows, you flow this integral onto a new contour on which the integral is very well behaved, it's monotonic, it's not oscillatory at all, and you can evaluate it numerically to very high accuracy and very cheaply. So we developed this method. It allowed us to do integrals which nobody could do before. And I just want to emphasize this is a really elementary thing. And if you look at our paper, we give, there's a website where we provide the code which can do two-dimensional integrals. We give a public code. Anybody can use this method to calculate an arbitrary oscillatory two-dimensional integral. And they're extremely accurate. Okay, so one problem we solved was gravitational lensing. This is a problem of great contemporary interest because it's been observed many, many times. So there's a field called microlensing where stars and planets in the center of our galaxy are lensing sources behind them. And in fact, the first calculations of this were done by Einstein. Einstein pointed out the phenomenon of gravitational microlensing and the formation of caustics. So he realized that as the source travels behind the lens, you will get spikes in the intensity of the received light at these caustics. Einstein thought at the time, and he makes some comment in his paper in 1930, this will probably never be observed because, it's too difficult. But it turned out that in the 90s, Bohdan Paczynski at Princeton realized you could see gravitational microlensing. And by now, it's become a real industry. So something like 2,000 microlensing events have been seen. due to stars and planets in our galaxy. And this is, in fact, one of the most promising ways of discovering planets now, is by looking at stars, background stars, and trying to see, to look out for these caustic curves in the intensity of those stars. So you just constantly monitor millions or hundreds of millions of stars and look for the effect of a planet passing in front of them. Now, all of that is done using classical ray optics, okay? And for a good reason. Nobody knew how to do the calculation for wave optics. It's more complicated because you have to take into account the phases and the interference between all these paths. But essentially, you have to do an integral, right? Where the one I wrote down, which is just a two-dimensional integral for a thin lens with some phi of x. And for a point mass, it turns out the gravitational potential is, the potential phi is just the gravitational potential, which would be gm over r in 3 dimensions, but essentially because you project out the perpendicular direction, it turns into a two-dimensional problem. And so phi is log x. So for a point lens in gravitational microlensing, when you perform the integral, it comes down to a two-dimensional integral with a log in the exponent. Okay, so it turned out the authors I gave above, this Nakamura and Deguchi, could do it for a single point lens. Analytically, you get a hypergeometric function, but it's not very informative because you don't know what to do next. So nobody was able to do the two-dimensional integral for more than one lens until we came along with this method. And when we invented this method, it made all these integrals very easy. So here's what happens with a binary lens. So on the left, you see the lensing, the intensity pattern that you would see if you scan the sky. If there was a point source, let's say at infinity, and then two gravitational point masses, for example, a binary in orbit, and most stars in the galaxy are in binaries, actually. And so this is a completely generic phenomenon. And of course, many stars have planets as well. So you really need to be considering more than one lens, typically. So in the picture on the left, this is what you would see in the ray optics picture, geometric optics. The leftmost bright point in the middle is one lens, and the rightmost one is the other lens. And then you see all this beautiful pattern of caustics. In the middle picture is the same lens, but now seen with wave optics. And so this is what we predict, the pattern we predict. It's much richer because you get the diffraction fringes, and there turns out the spacing of the diffraction fringes directly tells you the mass of the 2 point masses. The mass of the point masses is not possible to recover from the geometric optics picture, but it is from the wave optics picture. So if you want to measure masses, the way to do it is to use radio waves, which are relatively long wavelength, and make an interference pattern. And then this just directly tells you the mass of the point masses from more or less from first principles physics. And the right-hand picture is one made by my student, Job Feldbrugger, who I did this work with. And he's taken this one step further, which is to really consider three-dimensional lenses where you have multiple contributions coming in. It's not a thin lens anymore, it's a thick lens. And you see you get these wonderful intricate interference patterns. What we are now thinking about, so the forward problem, compute an interference pattern for any lens, that's solved. Now we can do that. It's straightforward for any lens. The interesting problem now is the inverse problem. Given some pattern seen by a radio telescope, what was the lens? Okay, and it's a beautiful, beautiful problem, completely unsolved, and I think we believe it will be solved using really some of these ideas. Okay, so for the last part of the talk, I want to tell you about relativity and some very fascinating features. Now, as I mentioned at the beginning, you know, my own perspective about fundamental physics has really changed. I started doing it when I was in the early 80s. And the big thing was grand unified theories. And then we had string theories and extra dimensions. And to sort of summarize, we got used to adding things. We thought the way to solve physics is to add more and more new physics. I would say the logical conclusion of that methodology was the multiverse. We added physics, new ingredients, to the point where they overwhelmed us. And the theory became completely unpredictive. And in cosmology, you probably know the popular idea of inflation, of which I am a skeptic, but inflation seemed to support this with the ideas of the inflationary multiverse and so on. My own point of view was, you know, and I've seen cosmology go from an unknown field where everything was uncertain to extremely precise field. We have wonderful observations now. What they've taught us is that the universe is overwhelmingly simple. It's not complicated. You can describe everything we know about the large-scale universe in less than 5 numbers. Okay, it's just amazing. And the ideas which have succeeded have been the simple ones. Einstein's theory of gravity, the vacuum energy, the dark energy, postulated in, you know, before 1920. Dark matter, I've already said, is probably one of the right-handed neutrinos. The density perturbations, what are they? They are Gaussian, almost exactly scale invariant. This is a very old concept, and simplicity has triumphed. Okay, so my own perspective is the world turned out to be simpler than we thought, and it's the same with the LHC. So I take that as a stimulus to go back in time and look at our foundational concepts in the field and see, have we perhaps gone wrong somewhere when we find these paradoxes, such as the vacuum energy being infinity? You know, maybe we're just looking at this the wrong way. And all of the problems, I believe the Big Bang singularity is another one. If we think more carefully about the Big Bang singularity, maybe we will understand how quantum mechanics and gravity resolve the singularity. So I've gone back to the foundations, and what I've discovered in doing that, partly stimulated by people like Claudio Teitelbaum, who very much is in that spirit, what I have realized is how much of modern physics is built on assumptions which were not questioned and which actually are quite questionable. In fact, Richard Feynman himself never believed in quantum field theory. You just have to read his writings to realize quantum field theory was a big disappointment for him. He had a much more geometrical view of physics. He really thought about particles and quantum mechanical particles. Those were the fundamental entity with geometrical world lines, okay? Quantum field theory saw as just this gigantic machine invented by Dyson that happened to give the right answers some of the time, and sometimes gives crazy answers like infinite vacuum energy, but it doesn't really take you forward conceptually. So, and I've come to this point of view. So I'm just going to give you a glimpse of some of this. So let's think about a relativistic particle. What is it? Well, it's like a one-dimensional universe. You know, we live in a 3+1 universe, but nature always used the same theme again and again. And the most elementary universe is one-dimensional, just the world line of a particle. It's a geometrical object. It lives in an embedding space, which is the external view. You could think about that like the God's eye view of the particle. The particle has its own internal view. It's like we are inside the universe, and it travels along its world line. So a particle is a parameterized world line. I think of it as a one-dimensional universe where the only dimension is along the world line. And it has something like a metric. So the length of the world line, if you parameterize it with lambda, the proper length between 2 points is tau of lambda d lambda. If you think about Vierbeins in GR, the tau here is an Einbein. It's the square root of the metric. It has to be positive. It is not allowed to vanish in order for the geometry to be well defined. And there is no meaning to tau being negative. So there's some very basic geometrical principles once you adopt this point of view. And it turns out to explain many features about relativistic quantum mechanics and in fact about quantum field theory, just to go right back to the foundation of the field, of what we mean by a particle. I want to emphasize there are two worldviews here. One is external, so it's us looking at the particle. We are not on the particle world line, we're looking at it from outside. The other worldview is from the particle itself. It has its own clock. For example, if it's a decaying particle, it will have a clock which tells it when to decay. There's an internal worldview, and this echoes cosmology. So in cosmology, you can try to describe cosmology using an S matrix, right? An incoming universe, an outgoing universe, and it really doesn't work well. The point of view we have is internal. We are internal to the universe. We're not external to it. And so when we try to gain insight from particle physics in regard to cosmology, we need to, the correct analogy is with the internal picture of the relativistic particle. So now I think this part is a bit technical, so I'm going to skip over it a little bit, just to say that relativistic quantum mechanics is a bit of a strange subject. It has remained controversial for many years, for good reasons. Even what is the Hilbert space, what is the inner product, has been debated. And essentially the introduction of quantum field theory put all of those problems in the shade. So people said, oh, we don't have particles, we have fields, and so let's not worry about the particles. The only way the particles come in are in the S matrix. So you send in some particles and some particles come out, and there it's just free particles. And we're not allowed to look inside the particle interactions. So this point of view was sort of, don't ask the question, it's not legal. And I think that has been the source of quite a few of our problems. So what we've done, and because of time, I'm not going to be able to give you many details, but what we've done is to revive quantum mechanics in space-time, not just in space, but in time as well, in a very, very conservative and in fact, in a way which is a very minimal way. So the inner product we use is the integral over space-time of two wave functions. And then you have to tackle all kinds of issues. You get infinities because the integral, psi is just on-shell solution, e to the I omega t with some Fourier mode. Then this integral is infinite. So you have to resolve this infinity. Turns out there's a very nice inner product you can use. It has different features to the usual Klein-Gordon inner product, which is associated with field theory. In particular, the Klein-Gordon inner product is not positive. And this got quantum mechanics into a lot of trouble, relativistic quantum mechanics, because it gave negative norms. And this was partly the motivation for going to field theory. But my point of view is that no, I think we probably lost something in that transition. One of the things we lost was a deeper understanding of antiparticles. Antiparticles really are particles going backwards in time. And this was realized by Wheeler. Feynman loved this point of view. In fact, it wasn't Wheeler, it was even before Wheeler. But the geometry of particles and antiparticles is recovered in this picture, which I am developing. So I think in view of time, I'm going to skip this, unfortunately. I'm very excited about it because it's extremely elementary. And in fact, I just wanted to mention, there's even a mistake in the Feynman and Hibbs, the famous book. If you look at their description of the quantum mechanical path integral propagator called K, there's a somewhat delicate issue, which is when you go to non-relativistic quantum mechanics, the Feynman propagator is, it's really the Green's function for the Schrödinger equation, time-dependent Schrödinger equation, is defined to be 0 for negative times and equal to this answer for positive times. And sometimes people call that causality, that you say something is, you can't influence the past, and so the Green's function should be 0 in the past. So now it's very interesting because in quantum field theory, the relativistic Feynman propagator, which by the way is given beautifully by this geometrical picture without any need for I epsilons, I should also mention. I epsilon is completely unnecessary to include. The path integral, the propagator is unique. It doesn't need a prescription to define it. And these oscillations basically take care of themselves and they define everything. So the relativistic propagator, there's a bit of a strange thing. How did that relativistic propagator, which definitely is not vanishing at negative times, how did it go into the non-relativistic propagator, which does vanish at negative times? And this was not properly understood. And in fact, if you read Feynman's book, it says it's not defined if TB is less than TA. It will prove to be very convenient to define it to be 0. With this convention, okay, right? Now, this is very confused. And I asked Claudio about this. I said, this doesn't make any sense. It's not, we had a propagator in relativistic theory, and suddenly we adopt a convention that it should vanish for negative times. And so his answer was typical. He said, well, guess who wrote the book? Okay, because it's Feynman and Hibbs, but actually Hibbs wrote the book. And so he was basically saying, don't blame Feynman for this. But in fact, it's very, very beautiful. The resolution is interesting, which is that we always propagate something. We can propagate a particle which goes forwards in time, or an antiparticle which goes backwards in time in this geometrical picture. And when you propagate it, you do an integral, and it turns out the interference between the particle going backwards and going forwards cancels. And that's why K is 0 at negative times. So in fact, non-relativistic causality follows from interference. And this, yeah, I think this puzzle remains there in textbooks and so on. So all I'm saying here is to emphasize that the foundations of the field have been confusing, remain confusing, and these confusions propagate into quantum cosmology, quantum gravity, even today. And that's why I'm so excited about the field, because I think if we can make progress on the foundations, it will resolve many of these many of the current challenges we have. We have studied the Schwinger problem. This is the next most first non-trivial problem. Imagine I have a particle traveling through space-time, but it's not a free particle, so it doesn't travel in a straight line. In fact, it travels on a hyperboloid if it's accelerated by an electric field. So here we have an electric field, assumed uniform in space-time. We have the electron. It's flying off to the right, being accelerated by the electric field. And then there's a very beautiful phenomenon, which is that it's possible for the same electron to travel backwards in time as a positron, to turn around in time, okay, which means it travels in a space-like direction, though actually the trajectory is complex at that point, but it travels a lot around in time, and then it goes forward again as an electron. And it's a very, very beautiful process which exhibits how this paradox, how do you create a particle from nothing? Well, what you do is you have only one particle, but you have it going backwards some of the time and forwards some of the other, and then it goes forwards. And so if I look at a fixed time at this picture, I seem to have two particles. One is negative and one is positive, but actually it's the same particle. And John Wheeler, when thinking about this, made a wonderful hypothesis, which is that maybe there's only one particle in the universe, and all it does is go backwards and forwards and backwards and forwards. And every time we see, and this explains why all electrons have the same charge. They're actually the same particle. And why positrons have exactly the opposite charge. All right, they're also the same particle. They just happen to be going backwards. So, and in fact, I have come to believe that is probably going to be the right story. There probably is only one particle in the universe. This predates Wheeler. There's this beautiful picture in Stuckelberg's paper in 1941, and it shows, the top right is a particle going backwards in time and then forwards, and he obviously understood this was pair creation in relativistic quantum mechanics. And so this is something which Schwinger formalized, and Feynman and others believed in, and this picture still sits there. It is described in quantum field theory, but in a completely non-geometrical way. In the particle picture, it's really beautiful. And yeah, so there's some other features of it I won't describe. We have a new paper coming out, which we essentially look inside the path integral and calculate what are called weak values. We want to ask what's really going on in that particle creation in an electric field. And so here's a little movie that shows you the charge density in space-time when viewed from the point of view of the particle, the single particle. So this is in its own time. And you see this interference pattern when the particle pair are being created. And this leads to real experimental predictions. One day we'll be able to see this in the laboratory and really view these interference effects occurring in particle creation. One reason to be interested in this, of course, it's a model for the creation of the universe. If you can create a particle out of nothing, well, maybe the universe can, in a sense, be created. And so we hypothesized that the universe, the Big Bang, is something like this. There are, in a sense, two sides to the universe. One is the particle, one is the antiparticle. And what you can think of is sort of one half of the universe traveling backwards in time, maybe contracting, turning around, and going forwards in time, i.e. expanding and making the universe. And in fact, this picture is what underlies our theory of the dark matter. So I'm not going to go into it in any more detail, just to show a picture, but this kind of foundational thinking is what I'm interested in. So I just want to end by going back to something very elementary, which is the path integral in quantum mechanics and what it means. Okay, so I will tell you we have some ideas for how to define it mathematically, which has, as I've already mentioned, never been done. Just before we do that, let's try to use it a little bit before, you know, just as it is. And I want to give you a picture of what's going on. So imagine I do a quantum mechanical path integral for a simple harmonic oscillator. So you can do this easily, standard result, but ask a slightly non-standard question, okay? So consider the path integral for an initial state, which is a delta function in x. The particle is at x initial, and a final state, which is a delta function in x equal to x final. So we can all write down the path integral. It's just an integral where you propagate from xi to xf in some fixed time t. Now we're going to do something slightly unusual, which is to calculate expectation values of quantities inside that path integral. And this notion was, well, we do it when we calculate Green's functions and so on, but usually we think of these as just devices, not really physically meaningful to look inside the path integral. The people who work on quantum foundations have, in particular Yakir Aharonov, have developed a theory called weak measurement. It's a very clever idea. It says what you do, you don't want to do a strong measurement because you collapse the system, collapse the wave function. Instead, you imagine another system coupled very weakly to the one you're interested in. And the second system, the coupled system, is really a pointer. It's called a von Neumann measuring device, but it's really just some instrument for measuring where your particle is. So you couple that pointer to the system you're interested in very weakly, so it doesn't disturb it at all. It doesn't collapse the wave function, and so on. All that happens is your original system disturbs the pointer. Okay. Now, very weakly, it turns out, because the coupling is weak. But what you can then do is repeat that experiment any number of times, and so that you get a statistically significant deflection of your pointer, which is responding to the quantum state of the system being measured, and it's really telling you what that system is doing. So in a certain sense, you can observe a particle weakly as it goes through the double slit experiment. There's nothing stopping you from doing that and make predictions as to what your observational device will see in terms of the two particles interfering. So it's a nice way of looking at things. One sort of trivial quantity you can calculate is the expectation value of a delta function of the particle. In other words, the density of the particle in space between this initial and final state at some time t. And this is the picture you get. So my harmonic oscillator is following the black curve. That's the classical trajectory. But the weak density is a highly oscillatory quantity, you may not be surprised to learn. These bands here are oscillations. It's positive, negative, positive, negative. The oscillations are extremely violent. And in fact, if you just looked at the point of this weak density is it allows you to compute any moment of the particle position at any time t. So it's kind of a complete function. That it's the equivalent of a probability density. If I want to know any moment of the particle at time t, I can get it from the weak density. So, but it's extremely oscillatory, and sort of at first sight you would say, I can't use this. The integral is so oscillatory it doesn't mean anything. But the Picard-Lefschetz theory actually makes perfect sense of it, and this interference all goes away. And so you can indeed predict all quantum observables from the weak density and from this pattern in spacetime. And this is how spacetime itself must emerge. You see, we live in a universe with a certain spacetime. Well, that's the black curve. The classical picture is the black curve. But of course, spacetime must be quantum, so it must be fluctuating. And away from the classical spacetime, all of those fluctuations cancel due to interference. And so using these concepts, we think we can see how space-time emerges from quantized geometry. Here's a slice through one of those, you know, let's say in the middle of the diagram, the slice through the weak density, and you can see the non-relativistic is the yellow curve, the relativistic one is the blue curve. And so you can apply all these concepts to relativistic quantum mechanics just as you can for non-relativistic. The last topic I want to talk about is, I promised you I'd say something about showing path integrals exist. I think in view of time, I'm just going to skip it and see if you ask me questions. It's very, very fascinating, but the upshot is it's all interference. Okay, interference makes the path integral exist. I'm going to skip these. The next steps, we want to understand non-perturbative effects in quantum field theory, in particular for real-time processes, for dynamical processes. Gravity, the problem of cosmology and black holes. This is, I am convinced, this is the way to resolve the black hole information paradox. It's quite simple to formulate it in this way. You've got to do a very difficult integral, but at least you know what you want to calculate. So I'm happy to say some words about that if people ask. In summary, I believe we know the basic laws of physics. All we have to do is become very good at doing integrals. So thank you very much for listening.
So thank you very much, Professor Neil Turok, for this very inspiring talk. And the first thing, traditionally, I ask everybody to turn on their microphones to a huge clap of hands in acknowledgement.
Thank you.
Okay, so we have already some questions, but before that, even to stimulate people to write down their other questions or think about them, let me give you an overview of the audience you had during your talk, because sometimes you have the sensation that you're talking to an empty room, but it was not.
Yes, it's
from all around Brazil, different states, as I said, from north to south, from west to east. So Amazonas, Pará, Tocantins, Paraíba, Espírito Santo, Minas Gerais, Rio de Janeiro, São Paulo, Paraná, Santa Catarina, Rio Grande do Sul, o estado do Pará, obviamente, é onde está o nosso... the Pará state is obviously where our graduate program is, where we had students, postdocs, teachers, and professors representing us, like Professor Jorge Cassimeiras, Manuel Eleutério. I'll say some names just because I think these webinars belong to a historical series, right? And then, I mean, I think it's important to register that. But not only from Brazil, right? We have people from abroad, like from Chile. So it's George Zanelli is with us, from Italy, Alexander Kamenchik, from India, Parto Majundar, from Spain, Diego Rubiera Garcia. And we had, from Brazil, we had many teachers and professors and postdocs as well, and many students from different federal and state universities and institutes from all around Brazil, right? From different areas of physics and also from different areas of science. And I'll just mention some of them: Alberto Petrov, Álvaro Nogueira, Carmen Gottfried, Jorge Matzas, Giorgio Torrieri, Ilia Shapiro, José Ademir Lima, Júlio Fabres, Kepler Oliveira, Leila Greff, Marc Casals, Marco Knaip, Múcio Continentino, Nivaldo Lemos, Rodrigo Fontana, Renato Ângelo, Sérgio Joras, Satis Kumar, V.H., Tomás Ferreira, and Wilson Zanquin. These people, they, I know them, right? Most of them. And they are from different universities from all around Brazil. So be sure, rest assured that you have talked to, you have given a talk to a wide Brazilian audience. So let's move to the
Muito obrigado.
Okay, great. Great. So let me start with a YouTube question done by Antonio Duarte Pereira Jr. So when you asked for a question, he wrote down, but there's a delay in YouTube from, you know, it's not a...
Yeah.
Okay, so he asked, can you comment on lattice-like approaches as causal dynamical triangulation? So he has explained. So
Great.
if it's okay, so it's about taking on this causal dynamic triangulations as a way to evaluate the path integrals of quantum gravity.
Yes, beautiful. So there is a lot of similarity in the sense that I would take the Lorentzian theory as fundamental. That's what we want to calculate. And by the way, I changed my point of view because I was working with Stephen Hawking, who was convinced about the Euclidean path integral. But through various reasons, as you think more and more deeply about it, the Euclidean path integral for gravity really doesn't make sense. It's not just because of the conformal mode and the lack of positivity of the action. It is at a more elementary level. The Euclidean path integral is just a meaningless infinity, unfortunately. So there's much in common in the spirit with Lorentzian approaches to causal approaches to the path integral. The difference is that they, in the end, use Euclidean techniques. Okay, so they want to put something on a lattice and get some answer which has a reasonable continuum limit. And so they use Euclidean techniques to get rid of the oscillatory phases. My point of view, I mean, in a sense, that's also what we're doing, but we're doing that analytically. You know, handling these oscillatory phases numerically is just impossible. So what you have to do is somehow transform the integral into something less oscillatory. That is what Picard-Lefschetz theory does for you. It flows the contour. So in other words, the theory itself decides what are the variables which are optimal. Okay, you don't prejudge that. So you start with your Lorentzian theory, you flow it. The flow means the original integral is, you're evaluating the original integral. It's just equal to the one you flowed to by Cauchy's theorem. So I really like that approach. It should enable numerical simulations of quantum gravity. As far as I know, it hasn't been implemented yet. So what I would say is don't discretize first. First flow the theory, then discretize your Lefschetz thimbles, because on those thimbles, it now looks like a very well-defined lattice gauge theory type calculation. You've got positive action, nothing is oscillatory. By the way, it's a very beautiful thing. You get a number of thimbles, each one with its own phase, but the phase is constant on every thimble. And so all of the interference is encoded in a discrete number of phases. And the kind of continuum part of the integral is now you know, over a bell-shaped function, which is very convergent, very nicely convergent. So yeah, this Picard-Lefschetz theory really captures the essence of the phases and preserves them, and so they will reappear in anything you calculate. They will show you the interference that is actually happening.
Okay, so thank you, Antonio, for your question. Thank you, Professor Neil, for your answer. So let's move to other questions. I'll pass now for questions in the Google Meet virtual room. So I have a question from Giorgio Torrieri. Giorgio, do you want to make the question yourself?
Yes, I will. I'll ask by voice. So one experiment, I would argue that quantum field theory is experimentally, in a sense, some effects which are specific to quantum field theory, which are absent in quantum mechanics, are experimentally seen. For example, anomalies. We know that there are quantum anomalies because of the way pions decay.
Yes.
And anomalies are really relevant to what you're doing, because what they are is the contour. The contour breaks some of the symmetries of the fundamental Lagrangian.
I see.
Yeah. So I'm asking, I mean, in your approach,
Yes.
the symmetry of JR is diffeomorphism invariant. Will the contour generally break it? It usually does. Yeah.
So yeah, that's a great question. I would say so far the only work I've really done in GR is in the context of cosmology. I mean, within this framework. So we wrote a series of 6 papers disproving the Hartle and Hawking proposal. And what we did there is we did something very naive, but it's all we could do, which was to treat the homogeneous mode of the universe, the scale factor, as if it is a single degree of freedom, and then to treat the inhomogeneous modes just in perturbation theory. So gravitational waves, scalar perturbations, we treat in cosmological perturbation theory. So this is a well-defined approach. It seems to give sensible answers if you ask sensible questions. Like if I give you a universe and I ask what's the amplitude to get another universe with some perturbation, it will give you a completely unambiguous answer. What it did show is that the Hartle-Hawking proposal, where you begin the universe and you only have one boundary, that failed miserably in this approach. It gave completely unacceptable answers. So I would say the question you're asking is a deeper one. You know, how do anomalies fit into the gravitational path integral? I think it's extremely interesting question. It's certainly a non-perturbative question. And I would almost turn it back to you. You see, the one thing we know about the universe, there are perturbations on large scales, right? There's Gaussian noise. It looks beautifully like the vacuum fluctuations of a quantum field. The form they take is scale invariant. It's highly suggestive they are something to do with anomalies. Okay, I could say more, but I will leave it at that. And I would say the question you're asking may be a very deep one, not just theoretically, but observationally. We see features of the universe which I think are so simple and yet so profound and challenging. You know, so one approach is you invent an infotron field and some pre-Big Bang era, and you go through it. Yes, you can fit them that way, but you end up with lots of free parameters, and you don't really know if what you're doing is the way nature works. So I tend to believe probably the perturbations will have a deeper explanation, which will just be gravity and the rest of physics we know. And I have some ideas along those lines. So for gravity, the whole notion of understanding the quantum mechanical consistency of this path integral, you know, it is really is one on the boundaries of what we currently can do, but it's definitely extremely interesting. I mean, I would refer you, although I don't necessarily believe the results, I think you know, some of the papers by Emil Motola, for example, on anomalies and their role in gravity are very interesting. And so there is a literature on this. I don't think it's reached any conclusion. It's not compelling yet. But personally, I think it's a very exciting question.
Okay, so thank you, Giorgio, for your question. Thank you, Professor Neil Turok, for your answer.
Thank you.
So
Thank
we have some more questions. Sergio Joraz wants to ask you about a reference. Sergio?
Yes, thank you, Crispino, for organizing this amazing series of lectures. And thank you, Professor Turok, for this amazing seminar. In particular to me, it was really interesting because I have used the same tools in my PhD thesis more than 20 years ago. So I used the steepest descent theory, catastrophe theory, and all that. It's really nice to see that again after so many years. So I wonder if you could go back for one moment to that deformation contour with the animation.
Yes.
So I can ask the question.
Oh, yes,
again.
please. Yes, of course.
So back then we were interested in the merging of the saddle points. So it's a different problem we studied back then. So my question is, the thick black lines are the steepest descent.
Exactly.
Right?
Exactly. Sorry,
so
no, sorry. No, that's not right. The thick black lines are the steepest descent and steepest ascent.
Of course, yes, of course.
Yes, right.
Of course, but my question is, the x-axis is not the steepest descent, right? So if you try to calculate this integral along the standard axis, it won't reach a correct value because of exactly this, right?
No, it will reach a correct value.
But you have the experience.
Wait, so this was the point I made about smoothing, okay? So if you take the original integral along the x-axis, and just to remind everyone, it's this integral. So I'm calculating e to the I phi of x from x going to minus infinity to infinity, right? And it's very challenging because, because the integral is so, it goes like x squared, right, in this case. Quite how do you do this integral? So the general prescription I'm proposing is the following. First of all, smooth the integral. So in this particular example, I would just take e to the minus epsilon x squared. That will be fine, where epsilon is small. And then I will define the integral as the limit epsilon goes to 0. More generally, you can say in any problem of interest, you choose some smoothing function which allows the oscillations to cancel as you go to infinity. Now, having chosen that smoothing function, then you have to prove that when I deform the contour from the chosen one, minus infinity to infinity, when I deform it, I get these arcs, these extra arcs at infinity, and I must show that those extra arcs contribute 0 in the limit of epsilon going to 0. So
that's the gray areas, right?
Yes, because basically because the function goes like e to the I x squared, what's happening is x is trying to go to e to the I pi over 4, so that the e to the I x squared will become e to the minus x squared. So the contour is flowing towards the steepest descent contour, but the extra arc at infinity, you've got an extra piece of the contour that you can prove contributes 0. Okay, in the limit as your smoothing goes away, that extra arc ceases to contribute to the integral.
So if you yourself, sorry, go ahead.
Yeah, so in fact, I haven't made a picture of this, but what you should really picture is the Riemann sphere. I'm doing an integral over the Riemann sphere. The point at infinity is the antipodal point to the origin, right, on the Riemann sphere. Now, when I introduce a smoothing function, it's an entire function which is only singular on that antipodal point. And basically, as I take the smoothing to infinity, the only effect of that function will be around the point at infinity. Okay? And so now you take your contour, which is on the real axis, flow it on the sphere, while leaving the endpoint at the point at infinity. Okay, and when you formulate it that way, the integral becomes absolutely convergent on the new contour. Furthermore, it's independent of the smoothing in the limit of the smoothing, scale going to infinity. And yeah, so what it's saying is that the original integral, when smoothed appropriately by an infinite class of possible smoothing functions, when you've applied any one of them and take this limit, you always get this answer. So what happens is you get a universal answer for the smoothed integral. And there's just no question this is the right answer. And by the way, I didn't point out in my talk, but you see there are 5 saddles in this picture. There are 5. And the one on the top and the bottom are irrelevant saddles. And that's generic, that whenever I consider some non-trivial problem, some of the saddles are relevant, some are irrelevant. And when you flow the contour, you find only the relevant saddles. You avoid the, and by the way, the Hartle-Hawking saddle turned out to be irrelevant. So they unfortunately picked the wrong saddle. The relevant one turned out to have the opposite sign in the action. So it's an easy mistake to make.
Just a final question. You mentioned a paper of yours as a basic reference.
Yes.
Would you say this one that I just put on the chat, 1909-04632?
Yes, I think that's the one about the radio astronomy.
Yes, that's the one.
Yes.
And I'm afraid he cannot see the chat because he's presenting. So if you allow me,
okay.
I'll jump
but it's
to
the one about radio astronomy.
Yes, exactly. Yes, exactly.
Okay.
Yeah.
Thank you so much again.
Thank you.
Okay. Thank you, Sergio. Thank you, Professor Neil. But let's move to the next question that comes from Satish Kumar VH. Satish, would you like to make it yourself?
Yes, thank you, Professor Crispino. Thank you, Dr. Turok, for the talk. It's very fundamental because I think you are proposing a new way of doing theoretical physics, if I understood right? So it's fantastic.
It's extremely old-fashioned, I must say. Okay.
But I've been thinking about. I have this book of Feynman Hibbs on my table, and then I've been thinking about this for a very long time. But
good.
It's definitely the future, not the old-fashioned, I would say.
Yeah, I believe so. I think all I'm really saying is, it's partly a psychological point of view. As I sort of hinted at, I feel the field went wrong, right? And one way I like to say it as a joke is the field went wrong when I joined it. Okay, because in the early 1980s there was so much enthusiasm to keep adding things, right? It did work up till that point. That's how we built the standard model. We did a new accelerator, new particle. Okay, just add it, right? And then by adding stuff, you hope to discover new symmetries. And that was the spirit of grand unification. You added new bunch of particles, and now the picture would become simpler. Ultimately, I think that strategy failed. And by the way, it's not hard to understand why. The worst mistake you can make in mathematical modeling, for example, of finance or biology, the worst mistake you can make is to add too many parameters, because then you lose predictive power. In a sense, I believe that's what happened in theoretical physics. We enjoyed adding new particles, and then it developed into adding new, many new particles and many new parameters. Then it became extra dimensions and strings and membranes and M theory and all that. And because we're more prolific than any other science, we took it further than anyone else, and we ended up with the multiverse. And that's we got what we deserve. So I think
that's true.
I think what I advocate is, let's go back. If we've gone wrong, let's go back and re-examine the foundations. And the people in the 50s and 40s, and these were very, very smart people. They often had really profound ideas which didn't survive, because it all became part of a big machine, which everyone just repeated the catechism. Okay, so the field, because of its success, got used to just repeating catechisms. You know, you just use the time-ordered product and you use I epsilon and, you know, everything will be fine. You calculate the S matrix, everything will be fine. And I think we've got to move away from those catechisms and really re-examine foundational issues. And this field of quantum foundations I mentioned, although it used to be very philosophical and probably not very concrete, I think it's evolved into an interesting place where they're asking deep questions about quantum mechanics in very concrete ways, which inspire experiments, which challenge other theoretical physicists, bring in quantum information, and so on. So, yeah, I hope we're going into a new age, right, where foundational thinking and re-examining the foundation becomes more and more accepted and normal. We should not take, you know, the what's in the textbooks as the final answer.
I agree. I think the best way to re-examine the foundations is to just find a new method of doing the same old things.
Yes.
Like you are trying to redo path integrals, right?
Exactly right. Exactly right.
We learned this from Lagrange, from Hamilton, by redoing Newtonian mechanics. We learned a great deal of classical mechanics, right? So
it's a fantastic,
same thing with the
fantastic
wave mechanics to Heisenberg to field theory. Yes, by developing new methods of doing the same old things, we will learn completely new things. I think that's my philosophy of doing research. I completely agree with that.
I couldn't agree more. And I think what really motivates me is that nature is simple, you know, and there's no better example than the observations in cosmology. We are seeing Einstein's theory confirmed to unbelievable accuracy, right? And so somehow nature is simple enough that we can, if we think hard enough, right, we can use what we know to understand the rest. And indeed, we just have to keep rethinking our basic tools to understand them more and more deeply. But the pot of gold at the end of the rainbow is beckoning, and nature is basically telling us, you know, I'm actually pretty simple.
I remember you reinforcing this point that nature is simple every time you get an opportunity, right? So just after Planck result, just after bicep, like every time you go and then say nature is much more simpler than we imagine.
Bet on simplicity. That's the one lesson of my career: is bet on simplicity, not on not on kind of artificial model building which introduces ad hoc ingredients. That you can just delude yourself. So it's very, very rich to go back to these old papers. I mean, if you read Feynman's papers on QED, you will not find anything you recognize in there about quantum field theory. He did everything in an intuitive particle way. And he didn't, you know, ultimately Dyson, beat him with formalism. But what Feynman had was intuition, and Dyson just had a machine. And I really think we need to re-examine things and get more intuition. The fact that Hawking is somebody who...
Yes, a good thing about Feynman's papers is there are only a few of them to read.
Yes. So Hawking had deeper insight. Hawking had deeper insight about gravity and quantum gravity than anyone. That's not debatable. But he went, I believe, and I came to this conclusion after a lot of worrying about this. Hawking came to the conclusion of using the Euclidean path integral. Why? Because of its success in quantum field theory, right? It's the basis of rigorous quantum field theory, lattice gauge theory. People had come to the conclusion that if you wanted to define things properly, you had to go Euclidean. And Hawking bought that and tried to import it into gravity. So these things are very well founded, but the only way to get out of that, channel is to go back to the beginning. Why did they do that? Why did they go Euclidean? And to re-examine what these very smart people thought, and hopefully to see where they made some mistake.
I will ask one last question related to what you just spoke.
Sure.
Speaking of the
Sure.
formalisms, right? And
Yes.
the Euclidean thing. So
Yeah.
Since you mentioned the Schwinger effect,
Yes.
is this Lorentzian path integral approach, the new approach to field
Yes.
theory?
Yes, it is.
Can you, does it
Yes.
mean it's inherently non-perturbative?
It is non-perturbative. That's the whole point, is we want to define
Fantastic.
this non-perturbative formula, right? And so the Schwinger effect is exciting precisely because it's non-perturbative. And what's so interesting about it is that the single particle picture, you know, is the most accurate way we have to capture the Schwinger mechanism. It captures it perfectly. So when I draw this picture, classically it is, so everything we do is in real time, Lorentzian signature, we never go Euclidean. What goes on is that you're trying to find a saddle point for the electron world line. Okay, so if it remains real and if the world line is real and obeys the constraint, so this constraint is the mass shell constraint, then you simply can't turn around in time, right? A particle going backwards in time must always go backwards in time. It's impossible to turn around. The only way it can turn around is if you allow complex saddle points, which are saddles for complex coordinates x and complex tau. So the question is, can I reach these saddle points by deforming the original integral into the complex plane of those variables, right? And the answer is you can, and you do. And these complex saddle points govern the whole process. But rather than it being Lorentzian, then Euclidean, then Lorentzian, you know, that's a very discontinuous thing. You've got a freedom to choose gauge. And you can choose a gauge in which tau, the world line parameter, is a constant complex number. And then you get this picture. So it turns out the saddle point solution to the Schwinger problem, which other authors described as Lorentzian, then Euclidean, then Lorentzian, there is a saddle point solution is complex and which tau is just complex, and it looks like this, and it turns out it's the simplest thing you could imagine. It's a geodesic on the complexified Lorentz group. It's really a unique simple curve on the Lorentz group that basically you boost the particle with that's what the electric field does, it accelerates it, and it turns out that the Lorentz transformation is a function of tau, and it's just a geodesic. You follow a geodesic on the Lorentz group. So it gives you a picture where this is really the simplest non-perturbative problem. It has a really simple solution, which is essentially that all these interference effects result in the dominance of a complex saddle point. That's what the complex saddle point sort of does so beautifully. It combines all the interference into a single classical answer, but it's a complex classical answer. And by the way, the same thing will happen in black hole evaporation. You can ask yourself, how am I going to solve this problem of black hole evaporation? Well, it's a tunneling problem, meaning that it's something which is classically...
Like Wilczek and...
Yes. The problem with
Parikh and Wilczek, sure.
Wilczek and Parikh, beautiful paper. The problem is they use square root actions and Hamiltonians, and these are very difficult to continue into the complex plane. Okay, so they are branch cuts and everything. So what they have is rather sketchy, and they never completed it because the analytic continuations are not clear. So, but I think what one should look for is when you form a black hole, you know, classically you form it and then it can never unform. So it's like this positron, it's going backwards in time, it can never turn around. So classically, you can't get out of the black hole. Quantum mechanically, you want to impose an initial condition that you have an infalling cloud of matter, and a final condition that you have an outgoing radiation. And then something is happening in the middle, which is the interference of multiple trajectories. It's just the same in this problem. We've got an initial condition of the positron going backwards in time, final condition, electron going forwards in time. Classically, they're impossible to connect, but quantum mechanically, we sum over all these paths, which are not on shell. They don't satisfy the equations of motion. And when we sum over all of them, we find a saddle point, which summarizes the process. So in the black hole case, there will be a complex saddle point, which allows the system to do the impossible, so that it formed a black hole. Then, in a sense, it goes complex, right? Indescribable, because it's really a superposition of many different spacetimes. And then what comes out of the complex spacetime would be the Hawking radiation, the final state of the black hole. So when you formulate that way, it's really not that difficult. What you must do is to find a complex classical solution of the Einstein equations, which is consistent with the initial condition and the final condition. And what's quite funny is nobody has even looked, right? So there is no work, at least none that I know of, looking for complex classical solutions of the Einstein equations, which might interpolate between an incoming cloud of matter and outgoing Hawking radiation. And I was lucky to share this idea with Hawking before he passed away. And I met him. I said, Hawking, I said, Stephen, this is an easy problem. We just have to solve a PDE, admittedly for a complex metric. But we know the initial conditions, which is ingoing cloud of matter. We should put some simple matter in, maybe gravitational waves. But at the end of the day, we just have to find a solution to a PDE. And if we find it, that will resolve all questions about black hole evaporation. Because and Stephen agreed. He actually agreed. He said, yes, if one could find that complex solution, you would have solved the problem. The nice thing about this is we know the equation, right? It's the Einstein equation. That's the equation to solve. We don't need brains. We don't need extra dimensions. We don't need holography. We've just got to solve a very difficult PDE. It may be that, one can also say maybe there's no such solution, in which case you really would need ultraviolet physics. You'd need to know about string theory or whatever to complete the theory and make it well-defined. But I would say there's no evidence for that at all. There's no evidence that we really need something beyond Einstein to solve this particular problem. Or maybe there's slight evidence. You could say that the super Planckian problem, maybe you could interpret that way, but I think by and large, that problem arises because people try to attribute to the horizon of an evaporating black hole, they try to pretend that it's a fixed, rigid, classical space-time surface. And it isn't. It's quantum mechanical. I mean, when it's evaporating, that surface is complex. So anyway, I believe that
thank you so much, Dr. Turok. I won't take much of your time. Thank you so much. I'll talk to you later. Bye-bye.
Thank you. Pleasure.
So thank you, Satish. Thank you very much, Professor Turok. So we have some compliments here. Thanking you very much for your talk. And well, I mean, and even our secretary was very, amazed by your muito obrigado pronunciation.
Oh.
Even compliments for that you got. But anyway, so far all the questions have been made from inside Brazil. Let us allow some person to make one question from far away from both of us. So it's Parto Majuba from India. Parto, do you want to turn on your microphone to make your question?
Yes, Louis, thank you very much. Am I audible?
Yes.
Very nice talk, Professor Turok.
However,
if you permit me, I'd like to play devil's advocate
Please.
And ask two questions. First has to do with the great success so-called success of the Euclidean path integral approach in the standard model, which has led to results which agree beautifully with experiment, with great accuracy. The question is, do you think if we could implement the Lorentzian path integral, we would get something different? Or any guesses on that?
It's a wonderful question, and there's no doubt that lattice gauge theory has been a huge plus, and the fact you can predict the spectrum of QCD is an enormous achievement. I don't think anything I am saying would contradict that. The one direction where what I'm saying may add benefit to the standard model is that currently we don't know how to formulate the standard model on a Euclidean lattice in the presence of chiral fermions. As you know, standard model has chiral fermions. So that is an obstacle. Now, that is often referred to in the condensed matter literature. Such problems are called sign problems. And there's quite an extensive literature of people trying to formulate theories which don't naturally have a Euclidean version. They try to, get around the sign problem. That's very important. What I would say is that the sign problem and this chiral fermion problem, it seems to me, and I haven't thought a great deal about it, I have to say, it seems to me those may be part of the problem of time. That the Lorentzian theory, has a time. That time is very important. It allows you to specify the initial wave function, the final wave function, something which you cannot do in the Euclidean approach, because you simply don't have access to that Lorentzian time. So, sorry, hold on one second. Hello? Hello, I'm on a talk. Sorry about that. I couldn't talk over the telephone. Where was I? So
it's about
So chiral fermions. Yes, we need to solve that problem. So in a way, the problem of real time in path integrals is a much bigger problem than the sign problem or the chiral fermion problem. So one would like to calculate things in the time in which we observe, not in Euclidean time. Especially if you do things numerically, it's more or less hopeless to analytically continue something you computed in. So essentially, you can't describe dynamics. My short answer to you doesn't let it, you say, doesn't lattice gauge theory do everything? Well, it does, except it can't describe dynamics. So if you really want to know what happens in an out of equilibrium system, and the universe is the ultimate out of equilibrium system, then somehow you've got to resolve this issue. With the path integral. So, but these things are all related. It's very intriguing that the limitations of the standard model and field theory as currently formulated, seem to always come back to a very simple issue: are you handling the interference properly?
Excellent. Thank you very much. I have another question, short question, related to what you mentioned about the black hole.
Yes.
Although I don't work in Euclidean approaches to the black hole entropy problem, but people do cite the work of Gibbons and Hawking as a successful approach in terms of the extrinsic curvature. And they seem to be getting the area law, Bekenstein-Hawking area law. But suppose you moved away to, well, with the black hole, you do have the problem that it's not homogeneous, unlike in cosmology.
Exactly.
would enabling the Lorentzian approach have any problems in that case? And would you still get the area law? Or is there a
Yeah, it's a very good question. What I can say is, it's one we thought of immediately because we worked on cosmology first because it was easier. Right. And then we got instead of getting the entropy of de Sitter space, right, which is from the Euclidean path integral, that's what Hawking and collaborators got. We got the opposite sign. Okay.
Right.
And it's not ambiguous. The sign is fixed, and the saddle point gives e to the minus, so it gives it negative entropy.
Mm-hmm.
And, so then naturally we thought, what about the black hole? I mean, is that Euclidean calculation reliable or not? And I thought about it for a while. I have to say I've not come to any conclusion yet. And so all I can say is it's not easy to go to do the Lorentzian path integral for the black hole entropy, or at least I don't know how to do it. The Gibbons-Hawking work is extremely elegant and it's compelling in a certain sense, but you have to realize that it relies on the existence of a path integral. It relies on a path integral which does not exist. This is rather clear.
Yes, actually, morally speaking, I totally would agree with you because I was never comfortable with Euclideanization of space-time.
Right. So, and if you ask Gary Gibbons, and I encourage you to ask him, what do you currently think about the Euclidean path integral? And Gary is the world's biggest critic. Okay. So he is a very honest individual, and he will tell you it makes no sense. Okay. So I guess one is hoping that the formal calculation they do is ultimately possible to justify in a Lorentzian manner. But he would hope that. I'm sure he would hope that. But
so that's something to work on, right?
Absolutely.
Thank you so much. Thank you very much.
Yeah, no, it's a pleasure. I mean, the trouble is the Euclidean formulation is so powerful because you're calculating a partition function. You can immediately get the entropy out of it. When you do a Lorentzian calculation, it's all much more delicate. You must put in an initial state, a final state. You're doing a dynamical calculation. What you would hope for is to get some measure of the volume of phase space, which is being occupied by the black hole. That would be some measure of the entropy. But you don't have the same tricks available that you have in the Euclidean, that you have in equilibrium statistical mechanics. Right. So, yeah, it's a very, very interesting question. I don't have a simple answer to give.
Thank you very much, Professor Turok. Thank you very much.
Thank you.
So thank you very much, Pato, and thank you, New, for the answer. So, well, I mean, there are, as I said, compliments here. So George Zanelli just wrote, thanking you for the wonderful and inspiring lecture.
Oh, that's
from Chile. And also, we are already with 2 hours, Professor New. So, I mean, you have to tell me what should I do. We still have some questions. I mean, should we go on with?
I think I am a little exhausted.
Okay, so
it's been a long day here. We had the International Committee of the Higgs Center this afternoon before this talk. So yeah, I'm a bit exhausted. I can't guarantee that anything I say will make sense.
That's okay. So maybe we should come to the end. I mean, I'm not sure if everybody knows that, but you're speaking from Europe, so right? So you are hours ahead of Brazil instead of being hours behind, right?
That's
so
correct.
I think we should stop here.
Okay.
But before I ask the comprehension of the people that made questions that could not be answered, but We had a lot of things, I mean, to think about, and I'm sure we'll be thinking about your lecture for the next, let's say, at least hours, but maybe days.
Thank you. Thank you.
So before we finish, I'll just ask just for you to let you know, we have still around 50 people from counting, you know, from Google Meet, YouTube. So they are really here listening to you, very interested. But before we finish, I'll ask everybody to turn on their microphones again for a final round of applause in acknowledgement for this wonderful talk we had today. Thank you very much.
Thank you very much, everybody.